All right, welcome. Today, we are putting on our detective hats to investigate a really fascinating linear algebra problem. This one comes straight out of question 5 of our source material, and we're going to crack two distinct cases by following the clues hidden inside the logic of matrices and subspaces.
So this is the question that really kicks off our first case file. And it's kind of like a magic trick, right? You take a matrix, you multiply it by itself over and over, and then suddenly, poof, it just vanishes. Okay, let's dive in.
So what we're looking at here is a very special kind of matrix. It's called a niltonput matrix. That's the fancy official name for this whole vanishing act. So before we start, really digging in and interrogating it, let's get the basic facts straight.
Okay, so what this means is, if you multiply the matrix by itself enough times, and that's what that little k stands for, it just becomes the zero matrix. Now, the really key thing to remember here is that our matrix A, it doesn't start as 0, but it ends up as 0 after you multiply it enough. This is the central clue for this whole investigation.
All right, first things first for any detective. We need to find its identity. And for a matrix, that means finding its eigenvalues. You can think of an eigenvalue as a sort of fundamental constant for a matrix. It tells you how it stretches or shrinks vectors. And in this case, all the evidence is pointing to just one single suspect.
See, by just following this trail of logic, we've basically cornered our suspect. We start with the most basic definition there is, the eigenvalue equation. Then we just keep applying the matrix over and over to its eigenvector v. And that's when we drop our key piece of evidence. We know that a to the power of k is 0. The whole equation just collapses. And since that eigenvector v can't be 0 by definition, the only thing left, the only possibility, is that lambda, our eigenvalue, has to be 0.
So, what does this all mean? It means this whole vanishing act literally forces the eigenvalue to be 0. There's just no other option. Any matrix that does this trick, that eventually multiplies to 0, can only have 0 as its eigenvalue. And with that, case closed on this first clue.
Okay, so now that we've identified our matrix's true nature, its eigenvalue is 0. Let's see if we can simplify it. A really common and useful thing to do in linear algebra is to diagonalize a matrix. It just makes it so much easier to work with. So the question is, can we do that here? Well, the evidence suggests that this matrix is hiding something. It might not be what it seems. But first, just a quick little consequence of what we just found. The trace of a matrix, right, that's just the sum of its eigenvalues. Well, since all of its eigenvalues are 0, the trace has got to be 0 too. 0 plus 0 plus 0, it's just 0. It's a cool little fact, but it's just a warm-up. Let's get to the main event here.
All right, to figure out if this thing can be diagonalized, we need to compare two different ways of measuring how important its only eigenvalue, 0, really is. So think of it like this. The algebraic multiplicity is how many times 0 pops up as a solution when you do the math on paper. In our case, that's n times, which is the full size of the matrix. But then you have the geometric multiplicity. This is about something more, geometric. It's the number of independent directions, or eigenvectors, that are associated with that eigenvalue. Now here's the rule. For a matrix to be diagonalized, those two numbers must be the same. But here's the catch. If the geometric multiplicity were also n, our matrix would have had to be the 0 matrix from the very beginning, and we know that's not true. So that means the number of directions has to be less than n.
And boom, there it is. The rule is simple. For a matrix to be diagonalizable, algebraic and geometric multiplicity have to be equal. We just showed they're not equal. So we've proven it. This inequality proves our matrix is kind of wearing a disguise. You can't simplify it down into a nice, neat diagonal form. And with that, case file number 1 is officially solved.
All right, let's open up our second case file. This one's a bit different. It's a standoff between 3 different subspaces living in Rn. We'll just call them U, V, and W. And the rules of this standoff are really strict. None of these subspaces can be inside of another one. That sets up a pretty complex scene that we need to figure out.
Okay, so our first clue, we need to figure out the minimum possible size, or dimension, of subspace W given the rules of this standoff. The answer is totally constrained by how it relates to U and V.
So, to crack this, we're going to use a classic detective move, proof by contradiction. Let's just imagine what would happen if W was really, really small. Like, what if its dimension was 0, or maybe 1? We'll see if those scenarios even make sense. If they fall apart, then we know the truth has to be something bigger.
Okay, let's put these theories to the test.
So if W's dimension is 0, what is it? It's just a single point, the origin. And that point has to be inside U and V, which, wait, that breaks one of our fundamental rules. So that's out. Okay, what if its dimension is 1? Then it's a line. Now, for its intersections with U and V to be different, one of those intersections would have to be the entire line W. But if that happened, it would mean W is completely inside U or V, which, again, breaks the rules. So, nope, both of these scenarios are totally impossible.
So, just like Sherlock Holmes said, once you eliminate the impossible, whatever remains, however improbable, must be the truth. The dimension of W has to be at least 2. If it were any smaller, the whole setup of the problem just falls apart. And with that, another clue is successfully analyzed.
All right, now for the final piece of this puzzle. We get a new condition, a new piece of evidence. W is the orthogonal complement of U. What does that mean? It means they are completely perpendicular to each other. The only thing they have in common is that single point, the 0 vector. Our job now is to prove that a certain, let's call it an alliance, between the intersections of these subspaces just can't happen.
Now, the expression we're supposed to be investigating looks a little messy at first glance, but that new fact we just got, it simplifies things beautifully. Because U and W are orthogonal complements, their intersection is just the 0 vector. So that whole middle term, poof, it's gone. It vanishes. So the real question boils down to this. Can the sum of the two intersections that are left equal the entire space Rn?
You guessed it, we're going to use proof by contradiction one last time. Let's just assume for a second that this alliance is possible. Let's assume they do add up to the whole space. We'll take a look. Both chunks of our sum are parts of the subspace V, right? That means when you add them together, the result has to live completely inside V as well. But hold on, if their sum is the entire space Rn, that means Rn itself has to be inside V. The only way that can happen is if V is Rn. And if V is the entire space, well then U and W would have to be contained within it. And that completely violates the fundamental rule of our standoff. So our initial assumption just collapsed. It can't be true. This alliance is impossible simply because the initial setup of the problem forbids it from ever happening.
And with that final contradiction, our second case is officially solved. We have definitively proven that this specific combination of subspaces, with these exact rules, can never, ever form an alliance that's big enough to span the entire universe of Rn.
You know, when you treat these math problems like cases to be solved, with clues and evidence and logical deduction, you start to see the really elegant and inescapable logic that's hidden just beneath the surface. It really isn't just about numbers and equations, it's about solving a puzzle. Thanks so much for joining me on this investigation.